Good day, everyone. Today, we are going to talk about disease burden time series data in healthcare and using machine learning and artificial intelligence for projecting future disease burden and care needs. My name is Deliang, Post-Doctoral Fellow in Department of Medicine, the University of Hong Kong. I am also member of SCAN 2030, responsible for AI machine learning-based disease burden forecasting. Based on electronic health record or epidemiological statistics, the healthcare-related data could be listed in the order of time. And based on this historical data, we can make forecasting to predict the future value. And the relatively accurate prediction can help us to participate future trends in patient demand, resource allocation, and disease prevalence, enabling early patient care planning and guiding the future epidemiological study. Let's have a look at the time series data. Time series data may have characteristics such as seasonality, which means repeating pattern or cycles in a time series that occur over fixed periods. They may also have trends, which means the overall direction and long-term movement of a time series. Time series could also have structural breaks. They are significant changes in the underlying patterns or relationships between a time series data set. These breaks can result from various factors, such as disease outbreak, policy changes, technological advancement, or socio-economic shocks, which leads to a certain shift in the data generating process. There are some structural breaks identification methods, including throw tests, zero Andrew tests, and rolling regressions. So what kind of time series are we talking about? Actually, we can classify the healthcare-related time series data by their granularity. Yearly data provide a broader perspective on long-term trends. They are common in population-wide epidemiological situation measurement, but they may not exhibit seasonal patterns. Because of the limitation of data point, detecting structural breaks in yearly data can be challenging. Monthly data offer a more granular view of how patterns are changing over time. This data may exhibit seasonality. A trend may also be present. Structural breaks can also be observed if patterns change over time due to policy intervention, change in clinical practice, or shift in disease outbreak. Daily real-time data provide up-to-date insight into disease distribution and healthcare coverage, enabling public health officials to monitor progress and adjust public health strategies as needed. The granularity of this data is small, which would contribute to uncertainty. The short-term random variation could interfere the identification of structural breaks. They may not exhibit seasonality. Individual healthcare data are the health-related information and records of single person. They can exhibit seasonal patterns influenced by factors such as weather changes, seasonal illness, and personal habits. Structural breaks in individual healthcare data can cause by subjective or objective reasons, such as the onset of illness, a major life event, or a significant change in personal habits. So, how to predict the future? Actually, forecasting models are using the characteristics of the time series when forecasting. Through training process, the forecasting model summarize and observe the time series characteristics by their own way into the model structure, and then produce the forecasting result. Except for these characteristics, different models can extract different patterns of the time series data. To be specific, the time series data can be classified as statistical forecasting model and deep learning forecasting model. Statistical forecasting models are grounded in classical statistics and rely on mathematical models to describe the underlying structure and pattern in the data, assuming that the data generating process follows a specific probability distribution or can be modeled using linear or nonlinear relationships. Such models are autoregressive integrated moving average, ARIMA, exponential smoothing, seasonal decomposition of time series, profit proposed by Facebook. As for deep learning forecasting model, these models rely on artificial neural networks to learn complex patterns and relationships in the data. They can be recurrent neural networks, RNN, long short-term memory, LSTM, and temporal fusion transformer, TFT. Let's have a deeper look at the models. ARIMA is recursive forecasting models. It is not only constructed by historical data and predictors, but also by combination of random variables as mean modeling. In a ARIMA model, time series should be stationary, which means the mean and the variance do not change over time. So integrated here represents an initial differential step to eliminate the stationarity of the time series. RNN and LSTM are neural network architecture originally designed to handle sequential data, which makes them applicable to handwriting recognition and text translation. In the context of time series forecasting, the input data is a sequence of historical observation ordered in time. The goal is to predict future values based on the pattern and relationships within the historical data. RNN and LSTM can process this time series data as sequential data and learn the temporal dependencies of the time series, then generate accurate forecasts. Transformer is a deep learning architecture based on a multi-head attention mechanism, which has been parently adopted for training large language model on large data sets. ChatGPT is one of its applications. Temporal fusion transformer, TFT, is designed to combine the multi-head attention mechanism with LSTM-based temporal dependencies, letting the model suitable for time series forecasting. Now let's have a look at the difference between the statistical forecasting model and deep learning forecasting model. For the deep learning forecasting models, they would be better at handling a large amount of data, capturing long-term relationships, and they will be more accurate, but they may be not easy to be interpreted. On the other hand, statistical forecasting model could be easier to be interpreted, and they can capture linear relationships and have less chance of overfitting, but they will be tough to handle complicated situations. This is the end of this talk. Hope you can enjoy and get some inspiration. Thank you.